Welcome back to the course Introduction to Green Process Engineering. Today we are going to focus on the topic of carbon dioxide. I will answer the questions whether we need to develop, respectively agree on a carbon management strategy. Then I will show you the most important sequestration technologies, and at the end I will discuss the requirements to build new infrastructure. In order to understand why we are actually discussing carbon management, we need to know something about the emission trading system, or short ETS. The ETS is a carbon market. It governs that and how much polluters have to pay for their greenhouse gas emissions. The ETS is intended to bring the overall emissions of the European Union down while generating revenues to finance the green transition. The path towards zero CO2 emissions is clearly given here. Companies have to act alongside this path. If they do not succeed in bringing down the CO2 emissions, they actually can no longer produce goods in Europe. Currently, the ETS covers emissions from electricity and heat generation, industrial manufacturing and aviation sectors, but also hard-to-abate emissions, for example from waste combustion, will be added to the system. If you want to get more detailed information about the emission trading system, then see the web pages of the European Commission. The ETS is a driver to reduce greenhouse gas emissions. Measures are implemented on different levels, the highest level being a carbon management strategy. It is clear that each country and companies that are part of the ETS need to have a carbon management strategy. The first step in a carbon management strategy is emission reduction by measures such as technologies or the use of carbon-neutral gases, mainly hydrogen. The second step focuses on hard-to-abate emissions, which refer to geogenic emissions as present in the cement industry or from waste incineration. The carbon management strategy includes carbon capture and storage, short CCS, carbon capture and utilization, short CCU, and carbon dioxide removal via technical or natural sinks. Let us start with a short insight into carbon capture and storage. The concept of CCS involves the capturing of CO2, the transport, and the main part, the storage itself. The storage either takes place onshore, where rock formations or saline aquifers are used for permanent storage, or offshore, where CO2 is pumped down to the sea. In each case, the storage locations are always located at a depth of at least 1 kilometer underground. Due to the pressure and temperature, CO2 is present as a liquid. Before we are able to store or utilize CO2, we need to capture the CO2. Technically, we just can capture CO2 that is available at point sources, for example at waste incineration plants, as already mentioned. Diffuse CO2 emissions, for example from agriculture or mobility, cannot be captured easily. Here, direct air capture is needed. Which technologies are currently available for the capturing of carbon dioxide from point sources? Well, the state-of-the-art technology is the absorption of CO2 in an amine-based solvent. The function principle is the solubility of carbon dioxide in the used solvent. You can see here as an industry example the flowchart of CO2 capturing of the waste incineration plant Twence in Hengelo in the Netherlands. CO2 is captured from flue gases in a solvent. The solvent is regenerated by heating it up, which decreases the solubility of CO2 and releases pure CO2. The CO2 is then pressurized for temporary storage and for further transport to either permanently store the CO2 or for further utilization. Absorption is not the only option for carbon capture. Here you see an overview of technologies that are used or potentially are used for carbon capture. The function principle of adsorption is that CO2 is adsorbed on the surface of a highly porous material and then either via a temperature or a pressure swing, the CO2 is released from the porous material. Zeolites or metal organic adsorbents are used as materials, for example. In adsorption processes, the long-term operation is not yet proven. The next technology that can be used is the cryogenic capture of CO2, where CO2 is frozen and then released by increasing the temperature. The function principle of a membrane operation is the permeation of molecules through a membrane. If you do sports, then you often use functional clothing, which uses a membrane for the selective transport of water. For CO2, the function principle is the same. CO2 can pass the membrane, the other compounds present in the flue gas remain in the flue gas. Last but not least, there is the option of performing the so-called solid looping, where a carbonation, for example of calcium oxide, leads to the solid product calcium carbonate that is utilized as fertilizer or is used in construction. Actually, this technology already utilizes or stores the CO2. Carbon dioxide capture is the costliest step in the carbon management. Hence, efficient processes are needed. The energy requirements for all technologies are in the range of 1 to 9 gigajoule per ton of CO2. Absorption and adsorption are already at the technological readiness level of 9, meaning that they are in industrial operation. The cost and efficiency of the respective operation highly depends on the concentration of CO2 in the flue gas. The more concentrated the flue gas is, the more efficient is the process. It is clear that storing CO2 cannot be the only measure. The utilization of carbon dioxide to generate long durable products is the next step in carbon management. Here you first see the sources of CO2. After capturing the CO2, it is converted by technologies such as biocatalysis, photocatalysis, thermochemical or electrochemical synthesis to products for material, fuels and chemical production. The utilization path often uses methanol as an intermediate product. The last step is the end of life. Here, the concept of a circular economy leads to a closed loop of CO2, which is fed back into the carbon circle. Additionally, CCU and CCS, direct air capture, is needed to achieve the goal of zero emissions. However, this topic will not be discussed today. We already discussed that CO2 can just be captured from point sources. Point sources being responsible for roughly half of the overall CO2 emissions today. And it is also clear that we need a certain size of production to convert CO2 into products. Hence, a CO2 infrastructure, including a pipeline system, storage facilities and utilization facilities will be needed in the future. You now may ask if there are already at least plans to build such an infrastructure. And the answer is yes. Here you see the plan for the CO2 grid based on the Fit for 55 regulation of the European Union. Red are the point sources, green are sinks and yellow are terminals. Gray indicate the transport lines. Not included in this graph are the conversion facilities. In conclusion, you now should be aware that carbon capture and storage and carbon capture and utilization are costly, but a need to achieve zero emissions in the European Union. Further, the ETS system forces the industry to act. The need for a carbon management strategy was discussed, and then I also showed what the capturing and the storage looks like. Further, the conversion of CO2 into products, in the best case long durable products, as well as the need for infrastructure was shown. I hope this short insight into carbon capture, utilization and storage was of interest and you take the opportunity to also watch the other videos. Thanks for watching and see you soon!